see, number 20. Is also a pretty straightforward trig substitution. Now, when you have trig functions combined with this, of course, there's a lot of exceptions to this and other techniques you'll see in calculus 2 for certain trig functions. But what we're dealing with in this class, especially with sine and cosine, this is true. Tangent and secant would be a little different because the derivative of tangent is secant squared. Now, you have sine and cosine, and you know that they relate to each other individually as derivatives, with the derivative of sine being cosine, the derivative of cosine being negative sine. So the question is, which one is u and which one's du? Well, first thing I did was get this up into kind of a linear fashion up on one line and make sine to the -3. Well, considering the fact that du doesn't have exponents associated with it, or at least an entire term raised to a power. I'm not talking about it, for example, if u equaled x cubed and du was 3x squared dx. That's different. So the u would have to be sine, because therefore the du would be cosine. And remember, when you're defining u, you don't include that power. You save that power for after you've taken care of this. So the u doesn't have that -3, but when we set up the integral, you just make u raised to the -3 du. So you should do the power rule. -3 plus 1 is -2, divided by -2, plus c. And then, of course, you have to, your final answer must be in terms of your original variable. So you just replace sine in here and sine x to the -2, which certainly, on a handwritten exam, I have no problem with negative exponents. That wouldn't bother me. But if you're having to actually pick out an answer, it's possible you might see this, because if you make this 1 over sine squared, and sine squared and cosecant are reciprocal functions, these would be equivalent. 1 over sine squared is exactly the same as negative cosecant, same as cosecant squared. 21. Now, okay, so basically what I did here is I let u be what's under the radical, which would be x cubed plus 5. And then du would be 3x squared dx. And then I didn't show the dividing both sides by 3, because I could just put this in here. Oh, not that thick. Could just put it divide by 3 here. There we go. So 1/3 du then would equal x squared dx. All right. So there's the 1/3 from the du right here. And the 2, of course, comes from this original problem. There's a 2 in it. And the x squared dx is all represented by the du. So we just basically end up with the integral 2/3 u to the -1/2 du. So we just do the power rule. -1/2 plus 1 is 1/2. Dividing that, so it's u to the 1/2 divided by 1/2, which flips over and becomes 2. Multiply that together, you have 4/3 u to the 1/2. Then replace u with what you had originally, and that will give you x cubed plus 5 to the 1/2. And of course, plus c. 22 is two separate trig functions, subtraction. With trig integrals, plus and minus, you can treat them as separate integrals, but not multiplication or division. So these can be split up, and I really didn't show a lot of work here, but let me explain what happened. They both have the same u, would be 2x, and makes du 2x, 2dx, and then we would divide by 2. So they're both going to have a half associated with it. So what basically happens here is you're integrating cos of u minus sine of u du. And that's the step I left out here. Maybe I can do something, change this real quick. Make this a different color. Let's say, I don't know, possibly. And I'll just put a u here. So in other words, the antiderivative of cos of u would be sine of u, and the antiderivative cos of u would be sine of u, but the antiderivative of sine of u is negative cos of u. Now, why do I have a positive here in front of that cosine? Well, that's easily explained because we have a negative right here in front of that sign. So that's what then just turns it into positive. So basically the antiderivative of negative sine of u would be positive cosine of u. And then you put the u's back in there, so that gives you 1/2 sine of 2x plus 1/2 cos of 2x plus c. Now this is an interesting kind of problem because it goes against the traditional normal substitution type problem. There's a technique that you would learn in Calculus 2 that would also do this problem. Doesn't make it easier than this, just a different way to do it. In my note, there's no real good name for this, but that's the kind of problem in my notes that I labeled as a special type of substitution. That's not really an official name. It's something that I just made up. So the problem with this one making it different than your normal integral, so you'd look at this and go, okay, I'm probably going to bet that my u is going to be what's under the radical, the x plus 1. But the problem is when you take the derivative of that, so I'm just going to move this around, not that there's anything wrong with this. You get dx, which is right. But see, the problem is with that, unlike your typical type of substitution, is that x right there, where I left the dot, is unaccounted for. So you have to have some way to account for that x. And the way we do that, in this method, this type of problem, is where we have u equals x plus 1, we solve for x in terms of u. That's kind of a weird thing you normally wouldn't see, but it's perfectly valid. So if u equals x plus 1, x could then be written as u minus 1. So we'd come down here, and now x is u minus 1 right here. The radical would just be u to the 1/2, because u is x plus 1, u to the 1/2 du. Now, because that u minus 1 is to the first power, we can distribute. Remember, you can't ever algebraically distribute through something that's not to the first power. So we can distribute before we integrate. U to the 1/2 times u is u to the 3/2. U to the 1/2 times 1, of course, is u to the 1/2. Put a minus in there. And so two separate u's. And we just apply the power rule to both of them. So u to the 3/2 plus 1 would be 5/2. So when you divide by 5/2, that will put the reciprocal 2/5 in front. 1/2 plus 1 is 3/2, which puts the reciprocal 2/3 in front. Then plus c, as long as plus c is in the final answer, that's all that really matters. It doesn't have to be in there right now, but it will be in the final. And then the last step is literally just replacing u with x plus 1. Now the problem when you look at textbooks and these kind of problems and you look up the answers, what they do is they'll factor out stuff and you'll get a completely different looking answer than what you would expect by working like this. Well, I would make sure that did not happen on a multiple choice test. I would make sure it looked like the answers looked like the way a normal person would solve it without going into doing a bunch of factoring. I probably show one in my notes. I'm sure I do, to where I just went through the process of simplification. Because I've had students ask me before, they try a problem like this, and if you look in the Larson book, they'll do some algebra steps, and a student will come to me and go, "Hey, I did this, and the book shows this. Where did I go wrong?" And actually, they didn't go wrong. It's just because the book answer are simplified. And yeah, so I make sure you don't have to do that. So if you do happen to run across something like that when you're looking at that, now you'll know why your answer is not exactly the same. Of course, don't let me stop you from having fun and trying if you want it. Not on a test. Certainly, that would take too much time. But just if you're practicing or something, you want to see if you can factor it and turn it into that answer that books often show, then you can give it a whirl. Certainly wouldn't hurt to sharpen up the algebra skills, but I don't make that mandatory at all. Now we have a definite integral involving substitution. So we have u equals, I'm going to let u equals x squared plus 9, because when I take the derivative of that, that's going to give me my x that's in front of the radical. So the derivative of x squared minus 9 is going to give me 2x dx. Of course, we would then divide by 2, right? So that would give me 1/2 du equals x dx. And there's the 1/2 right there. Now, there's two ways you can do these problems. I'm a big fan of changing on these definite integrals, just changing the limits of integration. And that prevents you from having to go back to x at the end, because if you don't do that, and oftentimes students will mess up because they'll do this u and then they'll put the original limits in there, 5 and 3. If you don't change the limits of integration, you have to replace the u back with x squared minus 9, which is what you have to do for an indefinite interval. But for definite integrals, that's not required. So what you do is, since u is defined as x squared minus 9, you take the upper limit, put 5 in there. So 5 squared, 25 minus 9 would be 16. Put 3 in there from here. 3 squared minus 9 would be 0. So now your limits would be from 0 to 16. U to the 1/2 du, and you never have to go back to variable x again in this problem. So now everything's u. The variables are u, the limits of integration are u, and we never have to switch. So I prefer that way to do it myself. But that's, like I said, that's not the only way. But you'll see every problem that I work out is done that way. Okay, so we have the 1/2 from right up here, the dividing by 2. Du over 2. Okay. And then we have to do the power rule for u to the 1/2. We've probably seen this one enough times already in this. So that's going to be, so there's the 1/2. So it's going to be 2/3 u to the 1/2. I think I've explained that about a million times already. Just using the power rule. Okay, so basically the 2's would cancel here. And we have 1/3 u to the 3/2. We plug 16 in there. 16 to the 3/2. And of course you can do it in a calculator, but square root of 16 is 4. 4 cubed is 64. Of course, zeros, anything will be zeros. So you have 1/3 times 64. So you would have 64 thirds as your answer. '25, same thing, definite interval. And you'd want to let the u be what's in the parentheses. Now be careful when you take your derivative here. Very careful. Because of the chain rule. So in other words, with a 1, just that's 0, of course. But it's real common and real easy for someone to say, what's the derivative cosine of phi t? They say negative sine of phi t. Well, that's almost correct, but not quite. Because the chain rule says you have to take the derivative of the argument. So that's where that 5 is coming from right there. So actually the derivative of 1 plus cos of phi t would be negative 5 sine of phi t. Now, it's just like I said in the last problem. I'm going to switch limits of integration. And we'll put pi in there, put 0 in there. So if u equals 1 plus cosine of 5t, I put pi in there for t. Cosine of 5 pi will be negative 1. You can calculate that if you want to, but the cosine of any odd integer pi would be negative 1, and any even integer pi would be positive 1. So that's basically 1 plus negative 1. That gives you a 0. And then when you put 0 in here, cosine of 0 is 1. You have 1 plus 1 is 2. Now don't be concerned that the limits revert, that the larger numbers on bottom than top. When you see definite integrals are always written from lowest to highest. This is okay because remember, we're changing the variable to u. So all bets are off. Originally in t, it was lowest to highest, but when you change to the new variable, it's like the last problem did stay lowest to highest, didn't it, I believe? Yeah, see, it went from 3 to 5 to 0 to 16. But this is perfectly fine. It's all because we've changed the variable to u. Now, and we have that negative 1/5, which I'll show you right here. I'm not going to rewrite this. Well, I guess I could. I've been doing it with these other ones. I'll show the divide by negative 5 here. So that's where so it's negative 1/5. Yeah, that's not too bad. All right, now, so what I did here, I love using this property of definite integrals. Like I said, you could have worked this out perfectly fine without doing it. But when I see extra negatives, I love to get rid of them by flipping those limits. It's not because it bothered me that the little smaller was on top and larger was on bottom. That didn't hurt my feelings or anything. I just want to get rid of that stray negative. So flipping this over, so what happened here is, so the antiderivative u squared would be u to the 3 over 3, and that became positive. So it's 1/5 times 1/3, which makes 1/15 u cubed. And because we changed our limits of integration, we do not have to go back to the original cosine of t and sine of t. All that stuff is plug in 2 and 0. That's why I prefer doing it this way. 2 cubed minus 0 cubed. So 2 cubed is 8. So our answer would be 8 divided by 15. 26, another substitution. Oh, looks like I already divided this one, didn't I? Pretty straightforward. U is x squared plus 1. Du is 2x dx, so you have 1/2 du equals x dx. Changing my limits, put 1 in there. 1 squared plus 1 would be 2. 0 squared plus 1 is 1. So we have the 1/2 right here. Now from 1 to 2, and we have u to the 5th du. Straight up power rule. So the 1/2 stays here, so u to the 5 plus 1 over 5 plus 1, u to the 6 over 6. And that gives you a 112 as your constant, so you put in 2. 2 to the 6 right here, 1 to the 6. That gives you 64 minus 1, which is 63 over 12, which on a handwritten test, it would be okay if you didn't reduce it. But if you were looking for an equivalent answer choice on a multiple choice test, you might be looking for 21 over 4. But I don't think that would cause you too much difficulty if you were having to look for that answer. So that's a pretty straightforward definite integral substitution. We have another one. So if you let u be t, notice I brought that up from the bottom to the top and gave it a -2. And let u equal t plus 1. That makes du equal dt, so there's no adjustments needed here. Plug in 3. 3 plus 1 would be 4. Then 1. 1 plus 1 would be 2. So our new limits will be, instead of 1 and 3, will be 2 and 4. So from 2 to 4. And then we have u to the -2. So your -2 plus 1 is -1 divided by -1. So that's what the negative sign is. So it's negative u to the -1. Okay, once again, I did the little trick of getting rid of that negative I didn't want by flipping those limits. So 2 to 4, 4 to 2. Yeah, it's perfectly fine to apply that, even though I have it. You see how I wrote the rule here as an integral sign. You can apply the rule after you've taken the antiderivative just with those limits. It doesn't have to be done up here. You know, it can be done right there when you're about to evaluate it. All right, so u to the -1 is just 1 over u. So now 2 is on top, 4 is on bottom, so we have 1 over 2 minus 1 over 4 gives us 1/4. So you see I'm just showing that property again down there. One of my personal favorites. Now it looks like we're moving into chapter 5 here. We're starting the logs and exponentials. So 28. Basically the derivative of the natural log of u is essentially u prime over u. So it's the derivative of what's on the inside divided by what's on the inside. So the derivative of 2x plus 3 would be 2 divided by 2x plus 3. So like I said, out the derivative of ddx of ln of u is u prime divided by u. As long as you know that, you're in great shape. Same thing here with 29. The derivative of ln of sine of x would just be the derivative of sine of x over sine of x. Derivative of sine is cosine divided by sine. Once again, that would be fine on a handwritten test. Possibly multiple choice. You might be looking for cotangent as your answer, but once again, that would not, if you knew you were looking for those kind of answers, it wouldn't be hard to come up with that. So the derivative of ln of sine of x is cotangent of x. Now apply laws of logarithms, log properties, to simplify this, then find its derivative, because this derivative would be a bit of a mess. Now, of course, we would not, if we did it without using these properties, we would get a completely different looking answer than this, but it would be mathematically equivalent. This would be a big old mess. You'd have to take the derivative of this inside. You've got product rule and chain rule, and then it would be divided by all this. It would be a mess. The log properties are terrific. So the log of a product of two things is the same as the sum of the two logs. And that's not just for ln, that's for any logarithm base. But since we're using ln, so ln, for example, ln of a times b would be the ln of a plus the ln of b. So that's the first split I did. And then the next thing you want to do is bring down any possible exponents you can bring down. You can bring down this outer exponent, this 2. So anytime the entire argument has an exponent, it can come down. That 3 can come down. Now you don't go inside the parentheses hunting for exponents. You can't go in there and extract that square out. Now this one you could get a little fancy if you wanted to. I probably would avoid doing that, but you could make a case, obviously, that x squared minus 1 is the natural log of x minus 1 times x plus 1, then you could split it even further. But that's all right. I think this problem, just doing this, gets the point across. It's not that difficult, just finishing it this way. So, but yeah, in case you notice that and were wondering, that's certainly true. And then you would have 3 times ln of x minus 1 plus 3 times ln of x plus 1. So now the derivative, so the 2 and the 3 just sit there. So remember, it's the derivative of the inside over what's on the inside. So the derivative of 3x minus 2 would be 3 divided by x minus 2. And then the derivative of x squared minus 1 is 2x divided by x squared minus 1 is fine. I put this check mark basically indicating that on a handwritten test it would be okay if you didn't go to the next step, which you see was not that big of a deal anyway. Most people probably would have gone to this step, but 2 times 3 is 6, of course, 3 times 2 is 6, so that's all that check is saying. Hey, this is okay, as is. Or actually, a lot of times in my notes I use the flag to indicate something's okay. And that answer's fine, even though my pink answer is also right, just one more step. Number 31, same kind of problem. Now, since all of that stuff on the inside belongs to that radical, it would be the same thing as if you put parentheses around it and raised it all to the 1/2 power. So since it's all raised to the 1/2 power, that 1/2 can come down using log properties right in front. Now, just like we had the log of a times b was the log of a plus the log of b, when it's division, it's subtraction. In other words, the log of a over b is the same as log of a minus log of b. I believe those properties are on my exam 3 formula sheet. Pretty sure they are. Anyway, so you just split this up to be subtraction. And I guess once again, like the last problem, you can certainly make a case for that factoring, but that's all right. So maybe I would avoid problems on the test if I remember so they don't factor, so it's not confusing. 4 plus x squared, remember, keep in mind that that does not factor. The sum of 2 squares never factors. Only the difference. So I split it up just now with subtraction. Minus, and we'll do the same thing at the 1/2 out in front. And the derivative of 9 minus x squared would be negative 2x over 9 minus x squared. And the derivative of x squared plus 4x is 2x divided by 4 plus x squared. You see I left the 1/2 to the outside, which I consider to be perfectly correct mathematically. But you know what I'm going to do? I'm going to go and see if I can do this without freehand it. So like that last problem, meaning if it was a handwritten test, I'll go ahead and put the flag here. Doesn't matter what color flag you use, that doesn't make any difference. In case you're wondering, blue flag, red flag, who cares? It's all the same. So I'm going to put this in a different color though, or actually I'll leave it that same. Well, I'll tell you what, I'll do this. I'll put it back in the same purple, meaning that that's okay. But then what I'm going to do here is just sort of show it as if it was. So if you kill this, well, actually the negative, I'd have to keep the negative, wouldn't I? I guess I could freehand that back in there. I don't have that color. I think I have that color pink on my palette here. I guess I can get it, but let me grab a new color. Is that pink right there? That might be it. Or is that too bright? We shall see. That wasn't right. Well, alright. Looked pink when I picked it. I mean, okay, that might be it. That pink didn't look right to me, but maybe it is right. See, that's a totally different color to me, but All right. That's all right. We're going to leave it as a weird thing. And then over here, the 2 would have canceled. Sorry, there we go. So that would also have been correct if we did distribute. That's going to bug me, so I'm just going to make the whole thing that color. Some sort of, it says pink, but it looks purple, light purple. I don't know. Yeah, there we go. That's fine. So this is, yeah, sometimes this doesn't look so smashed up looking on your original form, but whenever I convert it to this format, sometimes it kind of smashes stuff together. But see, the good news is you already have the, original. You can see it much clearer on the original form. Yeah, you're not depending on reading this. But it is, it's y equals 3x cubed ln of x. And we're trying to get the equation of the tangent line. So obviously for the equation of the tangent line, we need the slope. All right, get the derivative for the slope. And then we use y equals mx plus b. Now the 3, I'm going to go ahead and keep it with the x cubed. I mean, I'm treating f as being all of 3x cubed. I hate to leave it to the outside and have to remember to distribute it back at the end. And then ln of x will be g. So if I go f prime, the derivative of 3x cubed, that will be 9x squared ln of x. So that's f prime g plus f, which is 3x cubed, times the derivative of ln of x, which is 1 over x. And x goes into x cubed, x squared times. That's why I have a square here, because I didn't show that step, but it would have canceled. At this point now, all I have to do is plug in the 1, the x, which plug in the 1 to get the slope. So y prime of 1, I guess I could have been fancy here and said, I can make this, m, oops, ugly. There we go. Yeah, so there's an m kind of scares me. All right, that's the best I'm gonna be able to do here. So there's so that m means that's your slope. So just plug 1 in there, and you'll end up getting 3. And all right, so that's your slope. So you're dealing with y equals 3x plus b. So you have to then put in the x here. X is 1, and y is 0. So you put the 1 in for the x, 0 for the y, solve for d, and b will be -3. So therefore, your equation of your tangent line will be y equals 3x minus 3. Now, all right. So there's going to be a u substitution where you're going to let u equal 12x plus 2. Du would be 12x dx. So then 1/12 du equals dx. So come back up here. So my dx then is now represented by 1/12 du. That's my numerator. And then 12x plus 2, that's u on bottom. And the antiderivative of du over u to the first power. That's the key. The first power is ln of u. Any other power would be the power rule. Let me scroll back up there. And oftentimes students, when they're first learning these natural log integrals, they start seeing du over u to the anything. If they see u on the bottom, they want to call it natural log by instinct. That is not correct. It's only u to the first. Let me just hop back up here and find one for you. Well, here's one. See, that was a squared on bottom. That answer did not end up being natural log. It was u to the negative 2, so we used the power rule. And I'm sure there were others here. Yeah, see, that was x cubed plus 5 to the 1/2 on bottom, and it became negative 1/2 when you brought it up. Yes, for like this number 21, if that radical had not been there, if no radical is there, and no other parentheses or exponent, it would have been natural log. So oftentimes, so be careful. Don't just see anything on the bottom and think it's natural log. It has to be, the entire quantity has to be only raised to the first power. All right, now I lost it. Let's see, where was I here? There we go. Okay. So then we have basically 1/12 natural log of absolute value of u. So then you replace u with 12x plus 2. And then plus c, of course. Let's take a look at 34. This one's a little tricky. Now, this is a lot of time students get this idea confused. The difference between, and I have this as in my notes, so you can read in there, see it in there too. But in other words, ln of x in parentheses all raised to the fifth is not the same as ln of x to the fifth. All right, I'm gonna write this real sloppy here. I'll erase it, but this is what I'm writing here is not the same as what's in our problem. Ooh, yikes. That ln of x to the fifth, you can bring the 5 down. And that's correct. But not this one. You cannot do that. So what I did here, a little tricky, so you might be wondering, how are we going to get that little x on bottom? So I kind of brought that ln up first, power 5, and made it negative 5, going, gee, I wonder what would work here. How am I going to get that x on bottom? Then I think of this and go, wait a minute. If I let u equal ln of x, the derivative of ln of x is 1 over x. Bingo. Problem solved. And in fact, that's an absolute perfect fit here. In other words, no adjustments, no dividing or anything here. That's what I mean when I say perfect fit. So 1 over x, right there. So 1 over x 1 over x dx, I'm sorry, all that represents the du right here. And this is u to the negative 5. So power rule, negative 5 plus 1. And it's negative 4 divided by negative 4. So you have negative 1/4 ln of x to the negative 4, which is that's perfectly fine for a handwritten test. Very possible in a multiple choice test, you would just see it drop back down, raised to a positive 4 on bottom. Oh, like the answer is right here. That's for prime examples. But yeah, so you might have to recognize it looking like this. But it's interesting, if that was ln of x to the fifth, you'd actually bring that 5 down, and you would have had 1/5 on the outside, and then you would still let u be ln of x, but then it wouldn't have been raised to any power. It just would have been, well, actually it would have been raised to the negative 1. You would have gotten ln of x. I'm pretty sure there's one like that in my notes, so you can go back and look and see what I was talking about. All right, this is straight up substitution. You got to figure u is going to be the denominator here. One thing to keep in mind with integrals, du never ends up in the bottom of a fraction. U can be in the bottom because, you just lift it up and give it a negative exponent. But you would never have, this is impossible. You can have du over u, but you couldn't, this would make, let's just say u to the n, whatever it is, over like this as an integral. Kind of like, what in the heck? That would never be right. All right, so let u be 1 plus 7 sine of x. So du would be 7 cos of x dx. So I have to divide by 7. So there's where the 1 over 7 is coming from. So it's 1 over 7 du over u. And since that's u to the first power, that will du over u, same thing as saying u to the negative 1 du. That makes that natural log. So it's 1/7 natural log of u plus c. And this would be, therefore, would be 1/7 natural log of 1 plus 7 sine of x, absolute value, plus c. So I'll say this again. So if that denominator had been, either under like a radical or in parentheses raised to another exponent other than 1, natural log would not have been the answer. It would have been a different answer involving just the power rule. But this one's natural log because that's raised to the first power on the bottom. How about this one? And this comes off of that formula sheet that you'll have for exam 3. Now, the first thing I did was set up the adjustment here for this. U was going to be 3x, which makes du 3dx. So you have to divide both sides by 3. I don't know why this needs to be there. So you'll still end up with 3 on the outside. With the 18 that we have, right? And so there's the 18 right here. And then 1/3 just came out with it, so that's going to turn into 6 right there. And like I said, this is on your formula sheet. I changed the limits of integration. So pi over 12, 3 times pi over 12 makes pi over 4. 3 times 0 makes 0. So we have, and then the antiderivative of tan of u is negative natural log of cosine of u. This one won't have a plus c, of course. Remember, definite integrals do not have plus c's in their answer. All right, so now, so I have 0 to pi over 4. My integral is tan of u du, so it's negative 6, because it's negative right there. ln of cosine of u from 0 to pi over 4. Now this one's kind of interesting because I don't know why I did this when I was working this out, but it's nothing wrong with it. But every time you've seen me with this negative before, I always love to flip my limits of integration. But I can't honestly say why I did not do it this time. I don't see a mathematical reason, but that's fine. But you could absolutely flip those limits over and change that to positive 6 if you wanted to. So I just left the negative 6 out here. Natural log of cosine of pi over 4 minus natural log of cos of 0. That gives you cosine of pi over 4 is the square root of 2 over 2. Cosine of 0 is 1, and the ln of 1 happens to be 0. So we end up with negative 6. Now, it's a little tricky. I changed, and this is correct, but I could have done it without doing that, but I rewrote this square root of 2 over 2 as 1 over the square root of 2. That's the same thing. So this time I just basically rationalized the numerator instead of the denominator. So when I split this up, I have ln of 1 here minus, now here's where this comes from, it's property of logs. I'll kind of freehand this here. ln of root 2 is the same thing as ln of 2 to the 1/2, which then allows that 1/2 to come down like that. And that's what I have written there. That's this part right here. So that's where that comes from. All right, so then that just goes away to 0. So you have negative 6 times negative 1/2, which makes it 3 ln of 2. So you can kind of get different looking answers. I guess, on a multiple choice exam, when you work it out, you could just check to see which answers is the decimal equivalent of your answer. Then that's one way you could do it too. You could check it and see. And if you really want to have some fun with log properties, that answer also equals, that answer is the same thing as a natural log of 8. Because if you brought the 3 up to the top, it would be the ln of 2 to the third. So it would also equal a natural log of 8. Like I said, which you could check. Okay, see, the way I work that out, you can kind of go about that a little bit different ways, I think. So, but you should end up with the equivalent of 3 natural log of 2. 37, these derivative division problems. People hate this. This one has a lot more steps than I would ever actually ask on an exam. So look at, whatever I've given on the quiz or in my notes, especially my notes, have ideal types of problems. So what we do is, now I also showed we just jump ahead for a minute without going through the process. Well, I guess if I did it real fast, it'd be okay, but you could always Google, it's called synthetic division. That's an old algebra technique you maybe hadn't used in a while. But that only works though if you're dividing by like x plus something or x minus something. That would not work, for example, if this would have been x squared plus 4 on bottom. Then this technique I'm doing right here, this synthetic division, would not work. But you can look that up if you'd like to review look over synthetic division. But that's, like I said, that doesn't always apply to these problems. But you could certainly, if it did apply, you could use it. So we'll call this, how they say it in books, exercise left to the reader. You as the reader then can do some research on synthetic division. But let me walk through the division part here, because that's what you need to understand if you could not use synthetic. So let's see what we have. First thing you do, start with the largest power term of your divisor, and then the largest power of the part under here, which I think is called the dividend. I don't teach much elementary math, so I've forgotten the terminology. Divisor, dividend, quotient, remainder. I think that's right. If I'm wrong, no harm. So you look at how much does x go into x cubed, 2x cubed, which literally is saying 2x cubed divided by x would be 2x squared. So just like if you were doing division with numbers like you learned when you were a little kid, you take 2x, and then except that we're with numbers, not with expressions, but take 2x times x plus 4. So 2x squared times x, 2x squared times x makes 2x cubed. 2x squared times 4 is 8x squared. Now remember, division, when you're doing division, you're always subtracting, going down. So the first and foremost rule to remember here is that whatever you have underneath there, this 2x cubed, better also be the same, because the idea is this largest one cancels at each step. And the next largest one cancels, so you're always getting rid of this first one every time. But you have to be careful, because this is subtraction. That's where sometimes people make a mistake, because it's so easy to look at this 1x squared and 8x squared and add them together and call it 9x squared. That's not correct. It's 1x squared minus 8x squared, minus right there, negative 7x squared. Now these both have zeros below them, so when you subtract 0, nothing changes there. Now if 0 is on top of them, that'd be a different story. 0 minus something makes it the opposite. Now we look at x going into the new leading power, negative 7x squared. X goes into negative 7x squared, negative 7x, and then we distribute. Negative 7x times x is negative 7x squared. Negative 7x times 4 is negative 28x. And then, so right there in blue we have that, so we're subtracting, so of course the first one cancels. So negative 4x minus a minus 28x would be positive 24x plus 2. So this will be the last, whenever the power is the same, you're about to do your last division step. So x would go into 24x 24 times. So 24x right there, 24 times 4 is 96. We're subtracting, so 2 minus 96 makes negative 94. So that means our interval then would be our quotient, 2x squared minus 7x plus 24. And the remainder would be negative 94, but it's divided over the divisor. It's not just, so it's negative 94 over x plus 4. Okay, so the first three terms are simple enough, antiderivatives. I didn't actually show the word here, but I'll say it real quick, is that if you would let u equal x plus 4, so du would be dx. So you would basically have 94 du over u, the integral of that. So the integral of 94 du over u would be negative 94 natural log of u. So natural log of x plus 4 and plus c. So yeah, that division, if you can get the division right, you shouldn't have any problem getting the integral. Probably the division is probably worse than the integral. The integral terms aren't complicated. Now, so number 38, well, this gives people a lot of trouble because even, you'd be given this formula on a test, but that doesn't really, it's not that easy to apply the formula if you don't understand what you're doing. It's not just, direct plug and chug. It's not like saying, here's the quadratic formula, plug in A, B, and C. This is a little different. Okay, so this one's x squared plus 4x plus 9 for x greater than or equal to negative 2. Our function has to be 1-to-1 to have an inverse. 1-to-1 means it has to satisfy both horizontal and vertical line tests. So a parabola would not be 1-to-1 because you could just, crash right through it. So what this is telling you here is, but if you take certain sections of it, so x greater than or equal to negative 2 is likely telling us we're probably just taking the right half of the parabola. So that would be 1-to-1. It would pass just that segment of it without including the entire curve. So that means it would have a valid inverse. Otherwise, without that restriction, it would not. So what we're going to do is we're going to try to find the derivative of the inverse function, but we don't have to find the inverse function to do it. In fact, this one would be, I hate to say not impossible. You might be able to do it for this one, but it would be really messy and you wouldn't really want to do it. Trust me, even if you could. Many of them are impossible when we get these kind of problems. But don't even try. Don't worry about it. So to find f inverse prime at 14. First of all, I'm going to do this part right here. The f of b equals a. A is always the number of the 14, or whatever the number that you're given. The b is the number you have to solve for. So I take the original function and I put b in for x. I'm trying to find where f of b will equal a. So I put b in here, and a is my 14. Now the way I design these problems, and I would think, most books I would hope to do this way, but I design these where the answers are integer values. Now if it's a trig function, that might be different, of course, but where they're integer numbers, meaning that you're not going to have to do, actually you could, this one would be factorable. Let's just pretend like it wasn't, though. If you brought the 14 over, you could factor that. But let's just say it's just some weird deal or something or another. You don't have to solve it. You can just kind of get it by trial and error. Just try some numbers that you think are going to be kind of close and then see which one works. It's not going to be one where you have to do some weird extrapolations or weird quadratic formulas or finding the x-intercept on the calculator. These b values are going to be nice, easy numbers. I want that to happen. I'll make sure that happens. So let's just say I started with 0. B could be any number, any integer number that we're doing. I put in 0, that would give me 9, so that's not quite 14. And sometimes they might be negative, so you kind of, if you started using positives and you saw they were way off, you go to start using negative numbers. What if I put 1 in there? 1 squared plus 4 times 1, 1 plus 4 plus 9 is 14. Now there might be other numbers that satisfy this, which I think there is another one for this one, but keep in mind we have this restriction here. X is greater than or equal to negative 2. In fact, I think -5 might satisfy this also, but we can't use it. Let me see if that's right. -5 squared would be 25. 4 times -5 is negative 20. 25 minus 20 is 5 plus 9 is 14. Yeah, -5 would work, but there's only one number. There's only going to be one valid number in this. So it has to satisfy that. So the b would be 1. Okay, so once you find this b, which we just did, b equals 1, the derivative of the inverse at 14 is merely a matter of just finding 1 over the derivative of the original function. Original function at that b we just found. So let's look at our original function, pretty easy. So the derivative of that would just be 2x plus 4, right? And just create a little space there to show this part of the process. So all we have to do, there's a derivative. So f inverse prime of 14, by this definition, is 1 over f prime at 1, the b that we found. It is possible that b and a could end up being the same number. I generally try to avoid that for most of it. But it's possible that b could actually be the same number as a. Just want to mention that. So put in 1 for x, so it would be 1 over 2 times 1 plus 4. So the answer would be 1 over 6.